Well, welcome to today to the sequence and series, the geometric sequence and series part 3. Today we're going to look at everything to do with geometric sequences. So remember, just like the arithmetic, we need to set ourselves up. We need to know the certain terms, and we've talked about this earlier. So let's go for a quick recap. As an example, 6 would be our first term, which we write as a subscript 1. Our common ratio would be how we work out the second divided by the first, or the third divided by the second, etc. But before we get into that, let's actually graph this out and see what it looks like if we graph it. And there you go. That's what it looks like if you graph it. So, as I said, the first term is 6. The common ratio, you can use any pairing of terms. You can use the fourth divided by the third. I've used the third divided by the second. You get 24 over 12 is 2. So your common ratio is 2. And I know that if I want to say what is the value of the fourth term in this sequence, then it's simply going to be 6 times 2 to the power of 4 minus 1, 6 times 8, 48. And you can see that's what I've got there. So let's have an example. Straight from that book, find the 8th term in the geometric sequence. Now remember here, you need to work out what A equals. A is 5. What the common ratio is. You can use any pairings. You can do the second divided by the first. So 15 over 5 is 3. So I now got my A, I've got my R. I know I want the 8th term. So it's to the power of 7. So 5 times 3 to the power of 7. I get 10, 9, 3, 5. How many terms are there in this geometric sequence? A slightly different way of posing a nice question. So there's some 3 steps I'm going to show you here. First of all, always find A and R if possible. So I know the first term is 0.2. And here I'm not going to use the second and first because that looks complex. I'm going to use the third divided by the second. So I get a ratio of 5. I know the general last term. I can use this to say, well, the general last term is there. And if I know that the value of that equals 390,625, I can write my equation like this. So now I need to solve this equation. Okay, first thing I'm going to do is tidy things up as best I can. I'm going to get rid of that 0.2 by dividing it by both sides. And I end up with this, something to the power. Now I need to deal with that. The best way is with logs. So I'm going to log both sides. It doesn't matter what base here, it's base 10. I'm going to log both sides, and the beauty of that means I can deal with this n minus 1 and drop it down. I'm now going to divide both sides by log 5, and I end up with n minus 1 is 9, so n is 10. And the thing I can do is check. If I put the 10th term into this equation, would I get this large value? And yes, I do. Knowing that A is 0.2, my R is 5, so I do get that value. Finding the sum of a geometric sequence. Okay, now it's very similar to what we did with the arithmetic in how we deal with this. It's kind of nice, 2 strings of algebraic formulae, and you manipulate them nicely. So here we go. Here's my first one. So this is how you'd write it out as a sequence: A plus AR plus AR squared, etc. What I'm going to do is I'm going to multiply every term by R and then make sure that they line in sync so that they are the same underneath. Now, what's the beauty here is if I swap those around like that, I can get rid of virtually all these terms, barring the last one and this first one, by subtracting. I can just subtract them all away, and I end up with R minus 1 Sn, you see on the left-hand side here, equals ARn, AR to the n minus A. And then divide both sides by R minus 1. Take the factor of A out, and I end up with my formula there. It's really kind of neat. Now we can leave it like that, or we can write it as 1 minus R underneath, and we swap those 2 terms over there to be 1 minus R to the n. We do this when the common ratio lies between -1 and +1, and that's kind of really important. Okay, you need to understand that. That's a very important thing you need to know. But to just get rid of the idea of having negatives as well, if R is a small value, that's a neat way of dealing with it. So let's now find the sum of an infinite geometric sequence. So let's first of all consider things. This only works when the common ratio is between -1 and 1. And why is that? It's because each term will get progressively smaller. Think about it. Say you start with 100 and the common ratio is a half. You go 100, 50, 25, 12 and a half, etc. It gets smaller and smaller and smaller. So when r, the absolute value, is less than 1, then as n tends to infinity, then each term will get progressively smaller and smaller and smaller so that they tend towards 0, meaning this converges. Okay, what happens therefore to our formula here? Well, nice and neat. It's literally the r to the n goes to 0, so I'm left with a over 1 minus r. And that's a very nice formula to use. Remember, it only works when r is between -1 and +1. If it's not, and you're trying to find the sum of an infinite geometric series, you'll have more than one value. And so therefore you can't use it. It's kind of scary and fun. Let's look at some of the examples here. Okay, geometric sequence has terms 4, 8, 16, 10, 24. How many terms are there in this sequence? And find the sum of the terms. So the first thing, always find a, find r if you can. And you know that a is 4, r is going to be 8 over 4, 2. So you know those two values, and it's how many terms. So you actually know the last term, so you can use this formula again, and this is how they've done it. They've put it all in here. They know that equals 1024. Divide both sides by 4. Now you've got to the power, so log both sides. Divide both sides by log 2. Make sure, I mean, in this case, it's all equals. That's fine. But if you've got inequalities, you'll need to be careful with what you do with your inequalities. But in this case, it's an equal sum, so it's easy. So we know that there are 9 terms in this sequence. Now, for the second point, find the sum. Well, I'm literally going to fill the formula in here with what I know. And I get 2044. Find the sum of an infinite series. Now again, making sure that r, the absolute value of r is less than 1. Here we know it is because 1 over 2 is a half. We know the first term is 2, so I simply put it into my formula here and I get the sum is 4. The first 3 terms of this series, geometric sequence rather, it's 2, 1.6 and 1.28. And it says here how many terms will the sum be greater than 9? After how many terms will the sum of all of them be greater than 9? So I use my formula here, put in the values I know. I can quickly work out that r is 1.6 divided by 2, which is 0.8. I know that my a value is 2. So here, 2 divided by 0.2 is 10. That's where I get that term from. And it's when is this value here, when is the value of n such that this expression here is greater than 9? So divide both sides by 10. Log both sides, I've got this. Now this is an inequalities, okay? Now because log 0.8 is actually a negative number, whenever you're dealing with negative numbers in inequalities, timesing or dividing, you need to swap the inequality sign around. Remember that. Often catches people out. So divide those two logs and you get 10.31. Therefore, the sum will be greater than 9 after 11 terms. What about this one? Compound interest, often used for geometric questions. Here, you invest £100 at an interest rate of 4% per annum, compounded. So it's a compound interest built on each year, each year, each year. So I put a series out like that, the sequence out like that rather. Series is no point. You're not going to add each year on year like that. It doesn't work. So for the series, it has no practical point here. But for the sequence, we can see how it works out neatly here. So you can work out, well, how much interest will I have after the 10th year, etc., etc. And we've done a lot of this stuff at GCSE as well. What about this one? This one's quite interesting. A sample of radioactive material is decaying. Initially, it contains N nuclei. So at time 0, it contains N nuclei. The probability that any nucleus will decay in the course of 1 year is P. What's the expected number of nuclei remaining after N years? And this is an expected number. You'll come to this with other areas of maths when you get into the A2 curriculum. But let's just map this out. So I have A is my N subscript 0, so how many nuclei there were right at the beginning. And then after the first year, I multiply that sum by P, and that tells me how many I have in the second year. And you can see how this works here. But the question is, what is the expected number of nuclei remaining after Y years? After Y years. And that gets a bit more complex. That gets a bit more complex. So let's consider, because what I want to find out is how many are there remaining? How many are remaining? So I need to find out how many there are after the first year and take that away from how many there originally were. This tells me how many there are remaining. So that gives me my N1. And I can take N subscript O out just to tidy it up. Now I can do the same for the second year. So I can work out how many there are in the second year by saying, well, how many have I got now minus how many there were at the end of the first year. And that's what that tells you here. So again, I can take N subscript 1 out, but I can also now substitute, instead of N subscript 1, I can put this formula into here. And that's really neat because I get rid of some variables. So here we go. N2 is N subscript 0, bracket P minus 1 all squared. Because if I put that in there, these two brackets are congruent, so it's a squaring. Now you should notice the year here and that value correlate. They're the same. So therefore, after Y years, I can work out that it's N subscript 0, bracket P minus 1, all to the Y. Hope this has helped. Now it's over to you. Have a go at exercise 3.3. Come back to me if you've got any questions. Have a nice day.